Can everyone hear me? Excellent. All right, hi everyone. My name is Shlomo Priymak, and I've been working for Facebook for about 4 years now. I'm a production engineer. At Facebook, we have multiple teams that deal with MySQL, and I'm on one of them. So the three teams are, first we have the engineering team, the guys that actually hack MySQL and modify it to add various features. If you ever heard of WebScale SQL, or if you heard of the Facebook patch set, this is the version that we run internally. So we have a whole team that does that, proper software engineers working on MySQL. We have another team, which is about 4 people. It's pretty small. They're called the performance team. These are the guys that do actual database performance work, which is similar to what DBAs do in most companies. So they're the ones who actually engage with various customers of ours. The team I'm on, which is MySQL infrastructure, does everything else. So what does that mean? Our team is the DevOps in the most accurate definition. So we do everything from going to data centers occasionally, talking to the people in the data center. We manage some things that relate to hardware. We buy capacity. We decide how many millions of dollars to spend on hardware every quarter. Also, in addition to that, we write all of the software that runs the MySQL cluster. We have a huge cluster, like tens of thousands of database servers. I'm not allowed to expose the actual number, but it's a lot of machines. And we do everything that relates to managing that. So when you think about the MySQL cloud, we're the cloud. Our team is the one who does that stuff. And it's distributed in 2 locations. We have the California Menlo Park team. And that's like 6 people plus me. I'm managing the team right now. And we also have a team in Dublin, which is 6 people. So we're a pretty small team, and we do all this stuff. And I'm going to tell you guys today how we do that. Or specifically, one aspect of that, rather, how we back up all of our databases. So what I'm going to cover is some fundamentals about how we do backup, the challenges that happen when you back up this huge distributed system at a huge scale, the system we end up designing, and kind of how we implemented it, and probably cover some war stories here and there that are kind of amusing. So MySQL at Facebook. What does that mean? So Facebook uses MySQL extensively. Everything we do, almost every system has MySQL embedded in it. You probably don't realize, for example, that every time you send a message in Messenger, it ends up going through MySQL. Every single message. And we do that at like a huge throughput, very, very fast capacity. Everything is on Flash. It's very fast. Not only we do that for messages, but we also do it for everything else. So if you have your likes, your comments, your friend requests on Facebook, everything is stored in MySQL. In addition to that, we also have a lot of various smaller systems that also use MySQL, and they can vary in size. So it could be something small, like a few hundred machines. It could be something larger than a few thousand. It depends, but almost every other system also uses MySQL internally. So how do we do that? I'm going to explain that using an example you probably all heard of. So let's say your friend graph, your social graph. So we do sharding. If you ever heard of any lectures about databases in the past, it probably has been about sharding, how everyone does sharding. If you have a problem, shard it first. So at Facebook, we shard everything using something we call FBID, which is a 64-bit integer. And we have functionality that allows you to map this FBID to a specific shard. And these FBIDs, they're everywhere. So for example, if you look for your Facebook account through the Graph API, you'll notice that you have an ID. So you have an ID, your friends have IDs, every connection has an ID, every message you send has an ID. So 64 bits is a lot of space, so there's enough for everyone to have their own ID and all their friends and so on. So now that we sharded all this data, how do we actually map it to storage, to databases? So at Facebook, we run physical servers. We don't do virtualization of any sort, for MySQL at least. The way it works, we have a server. The server runs multiple MySQL instances. Instance is just MySQL running on a specific port. Most people that run MySQL, they run it on like one port. We run multiple instances for every single server. And we have multiple shards. A shard is just a database schema or a database in MySQL lingo. So it doesn't run by itself. Of course, we use replication. And we didn't want to just call this a replication chain, so we made up a new idea. We call this a replica set, because these are all replicas of the same data. And usually you have a master and multiple slaves that take, the master takes all the writes, the slaves take all the reads. Our databases are globally distributed. These members of the replica set live in many different locations across the globe, and we have a copy of our data in multiple locations. So here on the map, you can see all of our publicly available locations of all the data centers. So San Francisco is over there on the West Coast. The closest data center to us is Prineville, Oregon. And you have multiple others. You have one that we just built, I think, last year in Altoona. We have one in Ashburn, Virginia, Forest City, North Carolina, and one over there in Europe, which is probably the one that you guys are using when you use Facebook. You probably get to hit that data center, which is closest to you. So we have all these data centers. They all have a full copy of the data, or at least some of them do. But what does that actually mean? So here's the part that I like most about Facebook. That as a team that manages databases, I actually get to have access or kind of to feel what it means. So here's an example. This projector is not the best, but these are database racks. How many servers do you think you have in this picture? How many machines is that? Accurate. It's exactly 100 machines. Good job, Tomer. That's 100 hosts, and each one of these racks is huge. They're like, taller than me. They're 42-inch deep. They're humongous. I'm actually not sure if they're 42 because they're open rack. This is all hardware we manufacture ourselves. And I've been to these data centers. This is a picture from Luleå, our data center in Sweden. And actually, this host here, which you could have seen better if this projector was better, but these are database machines that we have used 3 years ago. We no longer have them, but this is old. So what does it mean when you say we have tens of thousands of hosts? Like, okay, you need more than that. So this is like 2 rows of servers. How many machines do you think you have there? Like something, these are very long rows. He's counting. No, so this is about 1,000 machines. I actually spent time try to count them. This maybe 1,000, maybe like 1,300, 1,400 machines, something in that scale. So when you actually need to have tens of thousands of machines, you can imagine you have server rooms such as this. These are all, by the way, if you want to see these are all public pictures of our Luleå data center. And you need huge rooms that host all these machines, and specifically, and these are just databases. So it makes sense that you have buildings like this one to host all this data. This is our data center in North Carolina. And what I like about this, let's see if this works. Can you see this red thing? Excellent. So what I like about this photo is this is a truck. This is like nice American-sized truck. These are American-sized SUVs or whatever it is. This is huge. This building takes like 5 minutes to drive around. So we need a lot of space for all these machines, and we have interesting challenges because we have so many machines, so many hosts, so much data. So let's talk about how we back things up. So I'm going to cover now a few fundamental things about how we approach backups in general, and later talk about various issues we've encountered, or rather how we solved one specific interesting issue. So we're on MySQL. For the most part, we use InnoDB. Actually, we use InnoDB for everything, but we're transitioning away from it for some of the use cases. If you have ever used MySQL, who here has heard of MySQL dump? All right, excellent, that's a lot of people. Awesome, so we actually use MySQL dump to do our backups. MySQL dump connects to MySQL database, basically runs a select star on your table and dumps it into a file. And surprisingly, to many people, that is what we do. This is the best way for us to back up databases. And it says here single transaction. That's because we use InnoDB, and if you supply this type of option, you get a consistent snapshot of your shard. We also modified MySQL actually to add something called logical read ahead to improve the way it reads data from disk. So on systems that are disk-based and not flash, we are like 10 times faster with reading the files because we read them using the physical order of the pages and not the logical order. If you're backing up MySQL, you probably should take a look at this option or using our version of MySQL because this is like 10 times faster if you use disk. If you use flash, your life is much better for many other reasons, but for some systems, disk is needed. So the question I always have immediately when I say we do logical dumps, people ask, why don't you do physical backups? Do like a snapshot, right? Like just do a snapshot, copy things away, or we use NetApp, why don't you use NetApp? It's a very common question, so instead of waiting for it, I'll just answer it right here. Here's a nice comparison. So first of all, if you take logical dumps, you can have external tools parse that data. So one of the cool things we do, for example, is we have ETL processes, and they need data from our user databases. We don't let them, just read through our entire database, select everything. That would be very, very slow, very inefficient. So instead, we have them read our backups. And they know how to parse them, they understand them, and this is how ETL takes its data. The size of a logical backup is also much smaller. Because you don't backup indexes, you don't backup various empty space on disk, you don't need all that stuff. If you backup using text, you can easily extract a specific table. If you need to restore that, that's a very common restore scenario versus storing everything. You can also debug corruptions if they happen. HDFS, which is what we use, and I'm going to get to it in a bit, is not perfect, and sometimes you can have corruptions, and if you need to restore something and the file is screwed, then you need to be able to read it, and if it's ASCII, it's much easier. And it compresses really well. So the only downside for doing logical backups is the time it takes to do them, because you actually need to do select and not just copy files away. So we do MySQL dump, cool. This is how we do full backups. We also did something pretty interesting, which is called differential backup. We have not open sourced this. It's internal to Facebook right now. The reason it's not open source is because we just didn't do it. There's no good reason. We can do it if someone wants to. It's going to be in Java, so I don't know if you want it open sourced. So differential backup. So differential backup in this case, in our case, means that we want to store our backups for longer. So since we take backups pretty often, we don't want to store the full version every time. So we want to take something differential. And if you use databases like Oracle or SQL Server, they know how to do differential backups. MySQL doesn't do that. So we had to create something like that. And the benefits are clear. So differential backup, this is a graph showing the percent of space taken by differential backups over time, and as a percent of the total database size. So you can see it grows quite slower than a full backup would grow. So the benefits are clear. It's a tiny percentage of the space, and you can store backups for longer. So how did we do that? Actually, it's pretty simple. It's similar to actual diff commands that you could run on your computer. So what we do is we take our full backup from, let's say, yesterday, and we take another backup today. And we just then run and scan the two files, outputting two other files. One for all the rows we deleted or are missing from the new backup, and one for the rows we have inserted. And you just generate these two files. So you scan over them if you have no change. And important thing, of course, the backups are for tables that are ordered in order of their primary key, which is very important. Otherwise, this is impossible to do. So this table has two rows, two columns, ID and city, int, and the city is a varchar, and it's ordered by the ID. So you scan two files, you see like San Francisco, there's no change. For ID number 2, Oakland changed to Santa Clara, so you want to say, okay, I deleted Oakland, I inserted Santa Clara. This is the difference between these two files. Here, Menlo Park has been completely deleted because 400 is the next one here, so there's no ID number 3. And Los Angeles has been added, since the 3 dots mean that everything here on is the same. So this definitely means that this row has been added. Yeah?
So this is basically a size optimization, right?
Yes.
Back in time is essentially the same.
Yes. The point here is to optimize size on disk. So you can do this as post-processing. You take the two files and you just diff them, and voila, you save tons of space. It is, yeah?
The data is immutable all the time, or because if you have a difference?
This is a backup, so once it's written,
No, but I
it's
have a question. Your data itself, is immutable, or you update records, developers?
are you asking if we modify data in our databases?
Yes. No, your row are immutable or mutable?
asking if we update rows. This works regardless. In this example, this shows you that the row was updated, and then it was an update is just removing and inserting, right, with different values. So it still works. Yeah. So the final output of this is going to be two files. One that deleted rows and one that inserted rows. So what do you do with this if you want to reconstruct the data? Well, it's pretty simple. What you do is a three-way merge. You read your old full backup. You still need to keep that one around. And then you read the inserted rows, the deleted rows, and you just merge everything to create the new backup. And this can be done online. You can stream all of these and do that. And I'm gonna get back to differential backups in a bit. Another fundamental is the fact that we back up binary logs. Binary logs are the record of everything that has changed on your MySQL server in terms of writes for a specific period of time. This is what is used this is what is used in the application. It allows us, by backing up these logs, we can do point-in-time recovery. Without that, there's no way. You only have your backup that you took like a day ago, and that's it. So you need to always back up binary logs. We also use global transaction IDs, or GTIDs. This is a fairly new concept in the MySQL world. If you're not using them, you probably should. They're nice. And the recent version of 5.7, Oracle added a way to more easily migrate to them. If you don't want to switch that version, you can use ours, which also has a migration path. So we back these up. And we back them up all the time. So what is our schedule? Like, how often do we actually take backups? So we back up everything we have every single day. So that means every single database shard gets a backup every single day, a full dump. We stream all the binary logs off of the machine, so you get them up to the whenever they streamed it off. We use semi-sync replication, so they end up on different hosts whenever a transaction is committed. So we back these up as well, and we stream them. So we need if we need the latest part, we can always get it. And we have multiple stages for our backups in general. We have HDFS, and we have another system that I'm not going to talk about for like offline backups. And the schedule looks something like this. You take a backup at a certain time. That will be a full backup. And then based on that full backup, you're going to generate 3 diffs by backing up the new another backup every day and then deleting it, right? And you do that every once in a while. So all these backups, they generate a huge amount of traffic. This is a graph showing the total amount of traffic going from our database servers to the backup system. This time here is the peak, is when we kick off backups around midnight. One immediately thinks, why don't you back up more frequently? We have a great trough there. There's not a huge amount of traffic. This is where the sun goes over the Pacific Ocean, so not many people use Facebook. So what's interesting about this is that the amount of traffic going into the backup cluster is huge. 3.5 terabits a second is humongous. And even when the system is kind of at rest, it still pipes half a terabyte of data into the system. And you'll see why network is such an important deal in a bit. And another thing I wanted to mention when it comes to fundamentals of backup at Facebook is the fact we do continuous restore. So we have a system that continuously reads every single backup, does it every 12 days, every single backup gets tested. So it reads the backup from the backup system and restores the latest backup to make sure it's valid and it's used. And it allows us to also improve the performance of the system because it does it continuously. So if it works well and we make it faster, we also make our emergency time restores faster. So I promised I'm going to get back to differential backups. So here's an interesting thing here. Differential backups in practice are actually a bit harder to do because, like I said before, you need 2 files, right? You need your old one and the new one that you just generated. So the first step would be take MySQL, run a full dump, put it into HDFS. Then you would want to read the 2 files, run them through the system that would create a diff, and dump the old HDFS file, the new backup file. Well, the problem is this doesn't actually work. This is how we intended to do this initially. We thought of running the entire thing inside of the HDFS cluster by using some MapReduce job. This is what was written in Java initially, but it just completely failed. It generated too much I/O. It generated too much network IOPS. And it took too long. The worst part, it took more than a day. So if your backup takes more than a day, this is unacceptable. We have to finish in the 24-hour window. So we actually did something neat. So something that's obvious here is that the full dump is going to be, the new full dump is going to be erased once you're done. So why bother even writing it somewhere at all? So what we did is something pretty interesting. We decided to do this in a streaming way. So what we do is we stream the new backup from MySQL. We stream the old one from HDFS from the day before, for example, or 2 days, 3 days ago. And we run them through the differ, just stream them. And this whole thing runs on the actual database machine. So it runs this like the differ on the host. MySQL pipes the backup into the diff. At the same time, it pipes the data from HDFS into the same thing, and it writes it back into HDFS at the same time. So this way, we never end up writing the full backups. This is a pretty neat trick. Without it, we could not have been able to actually make this work. So that's it for fundamentals and differential backups. This next part of the talk is about our backup scheduling system. So when I say scheduling, scheduling backups is a pretty tough problem. So what we do, we have an agent running on every single host, and this agent on that host is responsible for running the backups for all the shards that this machine hosts. If you have multiple instances, you back up these multiple instances using this agent. And it needs to orchestrate that. Since you have tons of machines, it's very hard to have like a single point of failure. You can't have like a backup manager that decides for all the hosts what they're going to back up. That just doesn't work. It's impossible to do. What we do is something a bit more creative. So what kind of decisions does a scheduling system like that needs to do? So I'm getting back to this slide of the world. So I said we have copies of databases in all these locations, or some of them, but we do not have backup clusters in all of these locations. Our backup capacity is actually spread between multiple regions. So actually, if we want to even take, let's say, the backup of our entire data set in one region, we cannot do that. We have to spread it around. But we don't have enough network capacity to actually pipe the entire Facebook data set across regions every single day. It's just impossible. I showed you the network graph. It goes up to like 3.5 terabits a second. That's too much. You can't do that. Even if you do it for the entire day, it's not going to work. So we need to be creative with how we consume network. And when a system like that needs to make decisions, it needs to make two choices. One is where you back up to, meaning which HDFS cluster in this case you would actually send the backup to. And the second thing it needs to do is what machine would be doing this backup. Because you have multiple replicas that are everywhere. One of them needs to do the backup eventually. So what are the goals for this type of system? First of all, we need to make sure that we equalize the way we use our HDFS clusters. We have many HDFS clusters. They're all large in size. We need to make sure that we use them equally so that we use our available backup capacity in a smart way. We need to minimize cross-region traffic. So that because if you suddenly start to copy things cross-region, you're going to just hurt actual production traffic. You don't have infinite bandwidth. Within data center, we have crazy, amazing network. It's super fast. This is why we have huge network spikes. It's fine. Across region, it's problematic. We need to make sure to not back up on broken replicas. That means, if you have a broken machine somewhere, or it has outdated version of the data, if it has lag, various problems, you need to make sure to avoid that. So the system needs to account for health. It needs to be consistent, so it doesn't flap around. So you can't one day back up everything here, one day back up everything there. If it starts flapping around, it creates unpredictable behaviors. So change needs to happen slowly. And of course, it needs to back up at least once. So we designed this interesting distribution algorithm. Basically what we do is instead of having a backup coordinator, we distribute the location that we would have globally in a configuration. We hash all of our shards into buckets. We make like 1,000 buckets that allows you up to 1 per mil of accuracy where you allocate things. Then you allocate these buckets to clusters, proportional to the size of the cluster. So here's the same thing I just said using pictures. So this is a server. It has 14 shards. You take the shards. You hash them around into multiple buckets. There's 8 here. Pretend it's 1,000, and every single shard has buckets, and every bucket has many shards. And then you make an allocation. So in this example, you have a 10 petabyte cluster with 1,000 buckets. So 10 petabyte total size for all the clusters combined, sorry. So cluster number 1 is like 1 petabyte, second one is 3, and according to their sizes, they get proper proportional allocations of buckets. So the one that's 2 petabytes in size gets 200, the one that's 2.5 gets 250, and so on. So then the systems, when they do the backups, they allocate the buckets to whatever range of buckets was allocated to that HDFS cluster. So bucket 20 and 30 are going to end up in the first one, bucket 200 and 400, second one, and so on. It's pretty simple, actually. Then the result of this is that we get a unified pool. So assuming that distribution is even and everything is great, you get very nice and clean distribution because of law of large numbers and the fact that everything is random. Right? Should work. Well, it doesn't actually work in practice, apparently, because we deployed the system. And so these are utilization graphs of our clusters. And surprisingly, one of these guys has been getting way more backups than the others. And this was in the early days when I was deploying this. I had no idea why this was happening. It doesn't make any sense. I thought it would calibrate over time. We actually introduced a new cluster here. You can see it's being turned up. These guys now need to store less. This one went up. What the hell? So that was kind of weird. Well, the problem was that not all hash functions are created equal. If you use Python hash, you're pretty much fucked. This is what you get. This is great allocation, right? This is 0 to 1,000, and these are like, I took like a random sampling of shards, allocate them to their buckets. You get ranges that are way lower than others. So Python hash is bad. It doesn't work. And of course, what is the right solution? MD5, that's it. This is what you get. With MD5, this makes much more sense. You do MD5, you do make it into an integer somehow and do a modulo, and you get something way more sane. And this is how it looked like. At the end, all the clusters happily agree, and they all store about the same amount of data, proportionally to their size, of course. All right. So next thing I'm going to talk about is how the machines actually decide when to perform a backup. So let's say you have this theoretical replica set. You have 3 machines, and they all need to decide who's going to do the backup. So let's say they somehow magically got a priority list. I'm going to describe the priority list in a bit. But let's say they magically got this priority list, and all of them know what are the best machines to run the backup. So every host by itself does the following. It looks for the priority list until it finds itself. So A here looks for the priority list and finds C to be the best candidate. It says, great, C should be doing this work, but let me double check on C. Maybe it's screwing up. So make sure that it contacts its host, contacts the backup agent of the machine, and says, hey, is this machine up? Is it running a backup? Is everything fine? If it is, great. It doesn't need to do anything. But let's say C is dead. So something else needs to do C's work. So it goes down in the list. It says, oh, awesome. I'm A. I'm number 2 in the list. I should probably run the backup. Great. That's pretty simple. But the tricky part is actually coming up with this priority list. And this is what I'm going to talk about next. So let's go back to this replica set, and ignore the replication topology because it doesn't matter. We back up from both masters and slaves. We don't need to only back up from a specific member of the replica set because they all contain the same data. And let's say in this example, we have HDFS clusters in some of the regions. So A has a cluster available to it named alpha, and C has a cluster available to it named gamma. So now what we do is we define distances. So the distance between 2 clusters that are located in the same region, let's say it's 0, it's very cheap. Our assumption is that traffic inside the region is very cheap because it's pretty much, it's not infinite, but it's huge. And cross regions, it's a bit more expensive. So you also factor in those distances between the different regions. So let's say a distance between B and backing up to alpha is going to be 10, B backing up to gamma is going to be 15, and A to gamma is going to be 20, so very expensive. We also then define priorities for our clusters. So you have some tiebreaker, so you know which cluster to prioritize when you generate the lists. So after you have the distances, and you have the locations of the clusters, which are represented by distances, and priorities for the clusters, you basically can create ranking functions for how you order that list. And the ranking function is simple. It's a tuple of first the distance, then the priority. Of course, in practice, this is much more complicated, but this is like a nice, this is the essence of the algorithm. So once you have this ranking function and distance priority, it's fairly easy to decide what you want to do, what you actually want to back up. So let's say M is the list of all of our MySQL servers. Age is the HFS clusters, so you have just 2 of them. What you do is you generate a Cartesian byproduct of the MySQL servers and the clusters, and then just order them. Oh, something here got cut off. It basically just means sort them by the ranking function. So if the list look like this, initially, so it's AN alpha, AN gamma, basically all the options, right? B alpha, B gamma, C alpha, C gamma. You order this, and then you get something that makes a lot more sense. And I'm going to go over this list now using this. Oops, this should not be animated. There you go. So if the list is C gamma, A alpha, B gamma, so if the first choice would be to back up locally, C would back up locally first. Let's say C was dead. The next choice would be for A to back up locally because it's located, it has a HDFS cluster in the same region. The last thing you do is have B attempt to backups. So first it will back up to alpha because it's closest one, and then it will back up, if there's no choice, to gamma. So this all makes sense. All right, so now you know how we decide to schedule something. You know how we choose which things go into the priority list. But what happens when this doesn't work that well? So here's a funny example. So let's go back to our theoretical replica set, A, B, and C. So this actually happened in practice. This was a replica set storing not user data, but some testing system. Anyway, backup runs on C. The problem is that when a backup runs, in this specific scenario, it caused load on the slave, and the slave had trouble keeping up. So the slave went zombie. It was lagging. The system said, OK, this guy is not healthy. Let me pick someone else to do the backup. And then B was doing the backup. C was also still doing the backup. But B was also doing the backup, double writing, because it thought it was dead. Then at some point, we have more slaves than 2. All the slaves were doing backups, and then the master started doing backup. So now we have a whole replica set. Everyone is doing backups. You have like 5 different backups being written at the same time. The system is not available. So of course, what's the fix for this? It's pretty simple. Just ask the machine it's already running a backup. Even if it's lagging, just let it finish. In this specific case, this was the only solution we could come up with. So next on, interesting war story. Yeah.
With regards to the previous slide,
Yeah.
you ended up saying, okay, I'll just ask machine C, but you need to have some sort of timeout for that because CAP tells us that you can't distinguish C being dead and C being lagging.
Correct.
So you need to have some cap.
So we know if it's lagging or dead. We have a way to figure it out. The machine is still available. It's just like the check that checked if it's healthy also checked lag.
Okay,
Does that make sense?
So the check itself is available and it tells you that the lag is just
Correct.
right?
Correct, yeah. The machine was available just like lagging. So cluster turnup. So those graphs you've seen before, where the utilization was going up, it's when we introduced new clusters. And when we brought up the system, because previously we would back up in only one region, but when this was introduced, we were backing up in many different regions. So what we did is we bring up a new cluster. And this is a new cluster in a new data center that we just built. And we start very slow ramp up. So I pushed some configuration change. I said, OK, 1% of the backups is now going to happen in this new data center. Great. Very careful, very small change. The problem is, even this tiny change actually started breaking the network. Network operations are coming to us saying, you're just transmitting too much data between data centers. You're affecting the cross-US links. So the weird thing was, the data was going from HDFS into MySQL, not being backed up. Like, what the hell is going on? Why would you? It was kind of weird. So after looking at it for a while, because usually when you're on the backup, you go into MySQL. But we forgot about our differentials. So what was happening here is that the system was pulling all differential backups across the region to write them locally. This broke things. We made a simple fix. We decided to only do differentials when the target has been the same as the previous run. So whenever you have a new full run, whenever the target changes, you generate another new backup. So we tested this for a bit after adding this fix. We go to 5%, 10%, everything looks fine, and I say, okay, screw it. Like I'll just go to 50 and then like 100%. Everything should be okay. I switch make the change. It's going up to 100. I look at all of our systems. Everything looks fine. The systems are running perfectly well. The backups are happening fine. We're happy. The problem is, this happened at I turned up at 8 a.m. We get side ops contact us. Side ops are the guys that sit inside the data centers that actually work on the actual physical infrastructure, on those servers I showed you before. So the story was something along the lines of, one of our guys was working near the big, how do you call these, circuit breakers? So like the ones you have in your home that if you use too much current, it jumps and cuts the power. So we have those in the data centers that just issue, a bit more than your home, like a few megawatts of power go through them. And they're pretty huge. They're about the size of this stage. They're humongous in size, computerized, all that stuff. So the problem was that one of these circuit breakers started to hum very loudly. And it coincided very closely with me turning up the backups. I'm like, shit, what did I do? It doesn't make any sense. So the problem is that when you plan a data center, you need to account for power usage. And the data centers that used to run backups had power usage accounted for these rows. You plan the rows, you put racks in specific rows. Every row has a specific draw. Every cluster has specific capacity. So the capacity was planned for machines that do not run backups. And there was a difference of a few kilowatts per rack. So the problem was that if we consume too much power, we're going to basically de-energize many rows, which is a very nice way to say we'll be completely fucked. Of course, it wouldn't actually happen with protections, but in theory. So we had an emergency meeting with the side ops guys, and we decided to come up with a simple solution. We just turned off a few racks. Luckily, we were sharing some of the capacity with some web racks. We're like, just turn them off, it's fine. They don't need them. Databases are more important. So this worked just fine. So the future. Everything I just told you is going to be completely irrelevant in a bit. Because we already have completely different plans of how we're going to do this stuff. So we're switching to row-based binary logs. These guys record previous value by default. They record the previous value of the row and the new value that you have. And you have the change log for every single row. So what is this row event? This row event that registers previous and next value is actually a very, very tiny diff. So what if you take many, many binary logs, process them, and create a diff offline? You can create those diffs without having a full backup, right? So if you take your full backup and apply diffs to it, you can create a new full without ever touching the database. So in theory, we could run backups only once. Wouldn't actually not need to do this whole thing. We could not consume all this network, not consume all this power, and do everything offline somewhere else. So we're not doing that yet, but that's going to come. So yeah, I'm pretty much done. The whole purpose of me coming here is so that someone can have some more exposure to what we do at Facebook. Of course, we're hiring everywhere in the world, in Israel, in the US, in London. So if you're interested, come talk to me, and I'm open for questions. So the question is, that I mentioned that we run the differential process inside of the MySQL, and whether it consumes resources. So the answer is that it runs as a process on the same machine. It's not part of MySQL itself. It's an external process. And no, it's pretty lightweight. Because all it does, it just streams files, right? It does something very trivial, or rather relatively trivial. It streams a file from MySQL. It streams a file at the same time from HDFS, and does a diff. It consumes a very low amount of memory. It's like 100 megs, and it calculates it on the fly. So it's pretty lightweight. Yeah? Have you considered another method of hashing? So we use range because it's easy. I can move things. The question is whether we have considered consistent hashing for the way we distribute the backups. So range allocation is very easy because I can create and control the configuration using configuration files that we distribute everywhere using something like Zookeeper. So I can just say, okay, now divert more to this cluster or less. Because let's say I want to say this cluster now gets penalized because I'm about to drain half of the capacity because we need to take those racks down. So I can control this very tightly. And ranges work perfectly for this. So, if you even move the slider a bit here, others get, yeah, it works fine. Yeah?
Beginning of your talk, you mentioned that you use Facebook radios.
Mm-hmm.
Usually people who develop systems use the UUID, which is 128 bits.
Mm-hmm.
You do that to be able to generate them in a distributed way. How do you generate the unique ID with 64-bit only?
So 64-bit. So the question is, why don't we use UUIDs for database IDs? So first of all, 64-bit is enough. You don't actually need to go 128. 64-bit is a huge range.
Like how do you generate them in a distributed
So every shard gets a specific allocation to it. That like some huge, many millions of IDs that can go to that shard, and then this is where it's written. Or are you asking how I can generate for a specific object?
Also, within the shard itself, if you need to generate few of them at the same time.
I can talk to you after the presentation. Yeah. We're out of time, so if anyone wants to leave, you guys are welcome to. How do you want to do it? All right, we're done.